Hey everybody, welcome back to chemistry. And there's a particular problem I want to go over that is on one of your Achieve assignments. And this is related to something called a combustion analysis and having to figure out an empirical formula for a compound based on that analysis. So if I can blow up the slide, the question reads as follows. An unknown compound contains only carbon, hydrogen, and oxygen. Combustion of 7.2 grams of this compound produced 14.4 grams of carbon dioxide and 5.89 grams of water. What is the empirical formula of the unknown compound? And I say insert subscripts as needed. Okay, so let me go to the board here and solve the problem. So what I'm going to do is this. So first off, let me just kind of talk a little bit about the kind of compound we're dealing with. And so in the problem it says we have a compound with only three types of elements, and they are carbon, hydrogen, and oxygen. So when you have a compound that has those three kinds of elements, it's called a carbohydrate. So let me give you an example of carbohydrate. So here we have a carbohydrate example. The molecule is called glucose, and it has 6 carbons in it bound to 12 hydrogens bound to 6 oxygens. And so here what I've done is I've sort of drawn what the structure of this molecule looks like. Now what will happen is carbohydrates like glucose will undergo combustion. And then when something undergoes combustion, what happens is it will react with oxygen like found in the air, and then you'll produce only 2 kinds of products, and those products will be carbon dioxide and water. So here what I've done is I have written the chemical reaction that this carbohydrate undergoes, glucose, and it will react with oxygen. So here are the reactants, and then when it reacts, it will burn. You'll see a flame from the sugar, and then you'll produce carbon dioxide, and you'll also produce water. Now, one of the things you may have noticed if you've taken a chemistry course before is that this is not what we call a balanced equation. So a balanced equation would make sure that for each different kind of element, we have as many atoms on the right side of the equation on the left side. And so to make sure we have that is we put coefficients in front of these formulas. But here I'm just showing you an unbalanced equation, and we can work with unbalanced equations for this kind of problem. Okay, just to point out, there are a lot of different kinds of carbohydrates, but they can all undergo combustion. So for example, here is the next carbohydrate I'm looking at. It's called ribose. It is C5H10O5. It has a particular structure similar to this, but it's just missing a carbon and oxygen and 2 hydrogens. Reacts with oxygen again, and then like all carbohydrates undergoing combustion, produces carbon dioxide and water. Now here's a final example. This is the carbohydrate sucrose, which is table sugar. Its formula is C12H22O11, reacts with oxygen, and then when it burns, when it combusts, it produces carbon dioxide and water. So one thing you can sort of see that is common with all these carbohydrates, they all react with oxygen, and they all produce only 2 kinds of products, and they are carbon dioxide and water. So what I want to do here is sort of generalize the idea. And the idea is this: if you have any kind of carbohydrate, so I've written C, H, and O, and then I wrote a little X subscript for the number of carbons you might have, a little Y subscript for the number of hydrogens, and a little Z subscript for the number of oxygens. Any carbohydrate here will react with oxygen to produce carbon dioxide and water. So in this problem, this is what's going on. They are telling you that you have some kind of carbohydrate here that has some particular formula, and that they tell you the mass of the carbohydrate that you have, and then they tell you it combusts with oxygen, and then they tell you the masses of the 2 products that you get, which are carbon dioxide and water. From this information, can you figure out what the original formula of the carbohydrate is? For example, is it C6H12O6, or is it C2H4O2, or C3H8O2, or something like that? So you have to figure out from this information we have in the problem, what is the correct empirical formula for this carbohydrate? Okay, so that is a bit of a difficult problem, but there are some things that we can do to sort of simplify the problem. That kind of makes it a little bit easier to solve. So let me tell you what those things are. So there are several assumptions that you can make that are important to solving this problem. So let me point out one of them is you see we have a carbohydrate here and it has carbon, for example. It reacts with oxygen, but I want you to notice that all the carbon in the carbohydrate is found in only one product, which is carbon dioxide. If you know the mass of carbon dioxide, what you can do is figure out, as I'll show you in a minute, how many grams of carbon are found in this 14.4 grams of carbon dioxide. Once you have found the grams of carbon there, because you assume all carbon in the carbohydrate goes into the carbon of the carbon dioxide, then the mass of carbon you found in the carbon dioxide will be the mass of carbon here found in the compound. Okay, so another assumption you can make is that all hydrogen in the carbohydrate will react and be found in one of the products, which is water. None will be found in carbon dioxide. It will all be found in water. So one of the things you can do is, if you know the mass of the water formed, what you can do is you can pretty easily figure out of this mass of the water formed, how many grams of hydrogen are found in the mass of water formed. And if you find the mass of hydrogen that's in the water, you can assume that is the same mass of hydrogen that was in the carbohydrate to start with. So one other thing that would be helpful to solving this problem is trying to figure out what the mass of oxygen is. And so we want to try to find the grams of oxygen. So you might ask, well, how do you figure that out? And so you can sort of see there's a bit of a complication in that we have oxygen in the carbohydrate, right? But we're adding oxygen in this chemical reaction, it may be an unknown amount, and then you're having oxygen split between these two compounds. So it's a little difficult to figure out by looking at the masses of the carbon dioxide and the water, because that's where you find oxygen, what the total mass of oxygen is. So what do? Well, there's a simplifying thing we can do to figure out the mass of oxygen in the carbohydrate. So you notice again, in this problem, the total mass of carbohydrate is 7.20 grams. If we find the mass of the carbon and we find the mass of the hydrogen, then subtracting the mass of the carbon and hydrogen that you found from the total mass should give you the mass of oxygen. So then that will give you the masses of the carbon, hydrogen, and oxygen. And from there, all you need to do is do the regular analysis to figure out the empirical formula, which means you take those masses, divide by the molar masses of the elements, and that'll give you the moles of these different elements, and then you divide by the smallest number, and then that should give you the empirical formula of the compound. Okay, so let's go ahead and try to solve this problem. All right, so what I'm going to do is I'm going to clear off some space here just to make it a little bit less confusing. Okay, so like I was saying before, we can figure out the mass of carbon in this carbohydrate by working out how many grams of carbon there are in carbon dioxide, because we are assuming that all the grams of the carbon in the carbohydrate will be converted to carbon in the carbon dioxide. So the question is, how do you take the mass of the carbon dioxide and figure out the mass of the carbon in it? Okay, so that's actually not too difficult to do, so let me show you how to do that. So we're going to take the mass of carbon dioxide that we had collected here, which is 14.4 grams of carbon dioxide, and we're going to get this into moles, so it's times 1 mole, and I know the molar mass of carbon dioxide is 44.01 grams, okay? So this is for carbon dioxide, right? So I'll be a little more careful here and put some carbon dioxide labels here, okay? And so the next step is we want to figure out, well, of these moles of carbon dioxide, how many moles of carbon are there? And you can see that for every 1 molecule of carbon dioxide, you have 1 atom of carbon. That means if you have 1 mole of carbon dioxide, you have 1 mole of carbon. So to deal with that, I'm going to write 1 mole of carbon dioxide over 1 mole of carbon, okay? Now, the next step to figure out the grams of carbon in this 14.4 grams of carbon dioxide is to multiply this by the molar mass of carbon, which is 12.011 grams of carbon over 1 mole of carbon. And so let's see where we're at here. So grams of carbon dioxide cancel, moles of carbon dioxide cancel, moles of carbon cancel. So you should be left with an answer in grams of carbon. So let me go ahead and work this out really quick. Equals 3.93 grams of carbon. That should be enough significant figures. Okay, so we have just figured out that in this 14.4 grams of carbon dioxide, there are 3.93 grams of carbon in it. And again, because we can make the assumption that all the carbon in the carbohydrate is transferred to carbon in carbon dioxide, what that means is we now know that there are 3.93 grams of carbon here in this carbohydrate. Okay, so the next step is what we're going to do is figure out how many grams of hydrogen are in the water, and that will tell us the grams of hydrogen in the carbohydrate. So how do we do that? We do something simple. We know that we got 5.89 grams of water. And then what we're going to do is convert that to moles, so it's times 1 mole of water over the molar mass of water. Okay, so far so good. All right, so the next step is, if you know the moles of water, you can figure out the moles of hydrogen. So recalling that there are 2 atoms of hydrogen for every 1 molecule of water, there will be 2 moles of hydrogen atoms in 1 mole of water molecules. And so we can write 2 mole of hydrogen over 1 mole of water. Okay, now the next step is to get this into mass of hydrogen. And so the molar mass of hydrogen is 1.008 grams per mole. So it's times 1.008 grams of hydrogen over 1 mole of hydrogen. Okay, so let me just work this out. And I get 0.66 grams of hydrogen. I think that's enough significant figures. Okay, so we just figured out that when you have 5.89 grams of water produced, you have 0.66 grams of hydrogen in it. And so we can see that therefore this carbohydrate must have 0.66 grams of hydrogen to start with, because all that hydrogen is transferred to water and nowhere else. So here in the carbohydrate we have 0.66 grams of hydrogen. Okay. So now the final step is we got to figure out the grams of oxygen. So let me remove this arrow here. It's a little unclear. Okay, so how do we figure out the grams of oxygen? So that's pretty easy to do. We know that the total mass here of the carbohydrate that was burned, submitted to combustion analysis, is 7.20 grams. We know that of that 7.20 grams, 3.93 grams of it is carbon, 0.66 grams of it is hydrogen. So you can just subtract these 2 values from the total mass to figure out the mass of the oxygen. So let me go ahead and do that. And I get 2.61 grams of oxygen. Okay, so we are now ready to figure out what the empirical formula for this compound is, because we know the masses of the 3 elements in it. So let me write this information up here. We don't need the total mass anymore. Again, we just have the masses of the 3 elements. So we have 3.93 grams of carbon. We have 0.66 grams of hydrogen. And we have 2.61 grams of oxygen. So at this point, all you need to do is just do the regular steps to figure out what the empirical formula of this compound is. So I'm going to go ahead and do that. So you may remember you have to take all these values of masses of these elements and convert them to moles. So it's times 1 mole over the molar mass of carbon. If you can look it up in the periodic table, it's 12.011 grams, 12.011 grams, okay. For hydrogen, same deal, divided by the molar mass is what you'll inevitably be doing, which is 1.088 grams. For oxygen, same deal, divided by the molar mass. I think well, we'll do it out to many significance figures, that's fine. So 15.999 grams. Okay, so let me go ahead and work out the moles. Okay, so now from this mole information, you should be able to work out the empirical formula. So you look at these three numbers of moles, and then you divide each of them by the smallest number, which is the moles of oxygen. So I'm going to divide this one by 0.1631, this one 0.1631, and this one by 0.1631. So with oxygen, you can see that we got 1 there. Okay, well, let me take 0.3272 and divide it by 0.1631. So I get 2.006. Okay, and we'll do this, 0.6584 divided by 0.1631. And I get 4.0367. So we now have a nice mole ratio of atoms. You can see that for every 2.006 atoms of carbon, there are 4.0367 atoms of hydrogen bound to it, and then we have 1 oxygen. But as you know, you cannot have decimals or fractions of atoms. What you have to do is you're going to have to take these numbers and round them to the closest whole number. So 2.006 is very close to 2, so there's 2 carbon atoms. Hydrogen, there's 4 of those, and then there is 1 oxygen atom. So the empirical formula should be C2H4O. Okay, I think your problem in the achieve is very similar, but with different numbers, and so I'm hoping this will be enough information for you to solve it. So thank you for listening.